PK/PD Associates, experts in pharmacokinetic and pharmacodynamic training for students, industry professionals, and other interested individuals. Hello, my name is Nathan Tuscher from PK/PD Associates, and this is a practical guide to calculating KEL, or the terminal elimination rate. The outline for this lecture will include a definition of KEL, calculation methods, and some common questions. The terminal elimination rate is a secondary PK parameter derived from the clearance and volume of distribution. It can be calculated directly from those parameters using the equation KEL equals clearance divided by volume. This parameter describes the rate of the slowest process in a PK profile. It can represent absorption or elimination, and multiple rates can be determined using a technique called curve stripping. However, we will not discuss that here. It's important to understand how different graphical scales affect the perception of data. Here's a plot of concentration time data on a linear y-axis. You can see that the concentrations fall in a logarithmic fashion. If we plot that same data using a logarithmic y-axis, we can see that they appear to be linear. This is the same data. This difference in scales makes it very easy to calculate the terminal elimination rate constant. First, we start with the data in linear format. Then we convert the concentration data by using a natural logarithm to give us data in linear fashion. We perform a linear regression using the log concentration and time data. KEL is equivalent to the negative of the slope estimated from the linear regression. The R-squared provides information on the goodness of fit of the linear regression, and the intercept is not needed for this calculation. So let's move to Excel and show you how to do this calculation. Here in Excel, I have some data. The first column contains the time data. The second column contains the concentration data. The graph below shows the concentration time plot in linear scales. The first step is to convert the concentration to log concentrations. We do that using the function in Excel called the natural log function. It is ln and then a parenthesis and then the cell that we want to change, in this case the concentration right next to it. So this column gives us our log concentrations. We can then perform the linear regression and acquire the slope and R-squared needed. First, the slope function can be used where we input the known y values and the known x values. And this is the slope function, slope and the known y values and the known x values. And that gives us the value of negative 0.0354. Then we can calculate the R-squared using the R-squared function, much in the same fashion, R-squared and the known y's and the known x's. We added a negative up here because it's a negative correlation. It will give us a negative number. We can then easily calculate the KEL by taking the negative of the slope as we've done in this cell here. If you set up a template in Excel, you can easily calculate the KEL for any data set. So let's return to the presentation. A common question is about how many points should be used. A minimum of 3 points is required by all regulatory agencies. Health Canada actually requires 4 points for some studies. Thus, 3 is the minimum. You can use as many as you need, but you should employ an objective criterion to find the optimal number of points. Maximizing the R-squared is the most common and the easiest to calculate. Another option is to maximize the adjusted R-squared, which I will explain on the next slide. Another question is whether or not to include Cmax. This is a personal or company preference. Most people do not include Cmax in the calculation. However, there is no reason it cannot be included. Remember, you're estimating KEL from the data. To calculate the real value, you should determine the clearance and volume of distribution and then calculate KEL directly. Finally, some may ask if you need to include Clast. In my opinion, the last concentration measurement should always be included. The absence of C-last may result in a biased estimate of KEL. R-squared describes the amount of variability explained by the linear regression. A value of 0 indicates a poor fit, or in other words, the time variable cannot predict the concentration using a linear equation. A value of 1 indicates a perfect fit, or by inputting a time value and using the linear equation, we can predict exactly the observed concentration. The adjusted R-squared is a method for correcting for the number of points used. It attempts to get the best fit line with the fewest number of data points. Thus, each additional data point results in a penalty in the adjusted R-squared calculation. Theoretically, some may argue that adjusted R-squared is better. In practice, very similar results are obtained with both R-squared and adjusted R-squared. Thus, the method you use is up to your own discretion. The key is to pick a minimum acceptable value for the fits. Common values are 0.7, 0.8, or 0.9. The minimum value provides a lower limit, below which you will need to report that the KEL could not be obtained. In summary, KEL is the terminal elimination rate, which is a secondary pK parameter. It can be calculated directly from clearance and volume of distribution. In addition, we reviewed how to estimate KEL using linear regression and the terminal concentration time data. Finally, we discussed the need for some objective criterion to define the best fit regression. For more training videos, please visit us at www.learnpkpd.com.